In the baking heat of the Australian outback, the most venomous snake in the world, the taipan, stalks its prey. 700 times as toxic as a rattlesnake, the taipan's bite packs enough poison to kill more than 60 humans. As it enters a rat's burrow, it's armed and dangerous. In an instant, it strikes. In seconds, the rat begins convulsing, its internal organs under assault by a complex mix of toxins that ensures its death. Venom.
If you're a snake, having venom is a great asset because it means that you can grab an organism, inject it with venom, and then let it go, and you don't have to fight with it.
For hundreds of millions of years, the world's top predators have relied on speed, or their size and sheer strength, to overpower their victims. But venom shifts the balance of power.
When we think of natural selection and evolution, we think of animals chasing each other and needing to be fast or needing to be strong. But venom changes the rules a little bit. It means that the small can defeat the big. It means that the slow can beat the fast.
Inside a tiny drop of venom, there's a minefield of toxins, a sea of exotic chemicals, some bafflingly complex, others so strange, it's taken scientists years and millions of dollars to copy just one. Venom is such a potent and successful weapon, it has evolved at least 10 separate times within dramatically different animals. From the stinging cells of jellyfish, like the Portuguese man-o'-war, to the dripping fangs of the funnel-web spider. There are venomous insects, venomous sharks, and even a venomous mammal, the platypus. So how did such a vicious weapon evolve? The answer may lie in a lab in Australia. Any investigation of venom must start with the animals that have killed more humans than any other: snakes. The scientist in charge is Brian Fry, the world expert on the evolution of snake venom.
It's a magnificent snake.
Collecting venom is laborious and dangerous.
All right.
For Fry, a day at the office can involve milking up to 50 different species of snakes. Every one of them a killer.
This is the Australian mulga snake. So this is a brown snake. What we've got here this time is a death adder. They're actually related to the cobras. So what we're doing is we're milking all of these snakes so that we can have the venom to study in the laboratory. You have to get the venom, obviously, from only one source. It's got a good little yield on him. Now, it's something you see a lot of variation in snake venom is the color of it.
Sometimes the process goes wrong.
Like I had one bite from one of these kinds of snakes where it bit, swung the fang, stuck it in, swung the other fang, stuck it in, swing, and just walked across my hand. I had a series of puncture wounds going across it. That was fun.
A dose of anti-venom saved Fry's life. But every year, 125,000 people die from snake bites. No anti-venom works for all snake bites because venom is so incredibly varied.
Venom is the ultimate in the movable feast, where not only do you get big variations from one species to another, but even within the geographical range of a single species, you can get quite pronounced differences in the venom composition, where they might have a different menu, you might say.
Fry has dedicated his career to working out why venom is so diverse and so deadly. Could its evolution be the answer? Fry already knew venom was a combination of deadly chemicals that worked in unison.
Think of it more of like basically a gang beating you to death with different shaped iron bars. It's a concerted, multi-dimensional attack on your body.
His quest to understand venom would take him 5 years. For Fry, just knowing it was complex wasn't enough. He wanted to know where all those chemicals came from and how they evolved.
It's a lot like sort of doing a molecular detective story. What we do is we break it down, we separate all the different components out into individual